In this lecture, I'm going to start the discrete time Fourier transform concept, right? So up to the previous lecture, we have solved some problems on continuous time Fourier transform. I hope that we got some basic idea about the continuous time Fourier transform and how to solve the questions from the continuous time Fourier transform. Now, when we talk about the discrete time Fourier transform, first we need to recollect what is the discrete time Fourier series. So the short form we can easily write DFS, discrete Fourier series. Now the Fourier series representation is always only for periodic signals, right? So when any periodic signal can be represented by its harmonically related complex exponentials. So that is the Fourier series. Now what happens when aperiodic signals are there? Can we represent like a Fourier series? So there is no possibility of that. So from the Fourier series representation, they found that we can represent in another domain, in frequency domain, that is discrete time Fourier transform for discrete aperiodic signals. For discrete aperiodic signals, so we can transform into another domain, that is frequency domain, that is called discrete time Fourier transform, right? So for aperiodic signals, we can find the discrete time Fourier transform to analyze the either system or signals, etc. And this discrete time Fourier transform is also, we can find the other domain, that is for periodic signals also. So generally the Fourier series only the representation in only time domain, right? The only Fourier series coefficient will be in somewhat in frequency domain, right? Now that is about the discrete time Fourier transform, some relation between discrete time Fourier series as well as discrete time Fourier transform. So Fourier transform discrete can be mainly we used for aperiodic signals, but we can find the Fourier transform for periodic signals also. So that we have seen already in the continuous time Fourier transform. Now one more comparison we need to make for discrete Fourier series as well as discrete time Fourier transform is this Fourier series representation is finite and discrete in nature. So that we have seen. Why? Because it is finite is it is periodic in nature. So if we draw the AK Fourier series coefficients, so those were they repeated in nature, right? Suppose this is 0, 1, 2. Suppose on n is equal to 3. So again it will be repeated in nature. So that's why it is finite but periodic in nature. And we said this is discrete. See, for discrete interval times we are having some discrete amplitudes, or amplitudes will be continuous, but there is a discrete intervals of time 3, 4, 5, etc. So the Fourier series representation is finite, or we can say periodic in nature, and discrete also, the discrete in nature also. But if I see the discrete time Fourier transform, a few minutes later we'll see this Fourier transform, discrete time Fourier transform is finite but continuous in nature. That is, discrete time Fourier transform also periodic in nature. So if I draw the x of j omega, generally it will be represented by e power j omega and omega. So it will be in periodic in nature, something like this. So we'll get something like this. So we'll see. So this is periodic in nature, but it is continuous in frequency. That is the only difference between discrete Fourier transform and discrete Fourier series. So it is discrete in nature, but it is continuous in nature. So remember this. So we may get question from this also, the comparison wise. And if you compare this DTFT and continuous time Fourier transform, there is again a similarity in continuous time Fourier transform. We got infinite series, right, and continuous in nature, but it is a periodic in nature but continuous, right? So that also you can remember. So continuous time Fourier transform is infinite in series, and infinite it is finite, but that is infinite in nature, but both are in continuous in nature. So that also you can remember. Now what are those equations to find the Fourier transform? So the discrete time signals generally we represent x of n, right? So what is the analysis equation? That is, if I want to find the DTFT, so generally DTFT of x of n can be represented by x of e power j omega, right? e power j omega, because exponential relation that is coming from the discrete Fourier series. X of e power j omega capital X is equal to sigma n is equal to minus infinity to infinity x of n into e power minus j omega n. So this is the Fourier transform equation to find, right? Fourier transform. So generally this equation is called analysis equation, right? To find the Fourier transform of given discrete time signal. So this is called analysis equation. Now once we find the discrete time Fourier transform, how to find the inverse Fourier transform? So inverse discrete time Fourier transform of this, we can say x of e power j omega is equal to x of n, and as we said it is continuous in nature, so we'll get the integration, but we need to integrate over one period, so that is 2 pi, right? And x of e power j omega into e power j omega n d omega. Now what is the difference between this omega domain? So we should get 1 by 2 pi in the denominator. So 1 by 2 pi integration over one period, that is minus pi to pi or 0 to 2 pi. So we need to integrate x of e power j omega into e power j omega n d omega. So this is called synthesis equation. X of n is equal to 1 by 2 pi integration over one period, because we are finding the inverse Fourier transform. This is x of e power j omega. This is called synthesis equation, right? So this generally these two pairs, this is 1 and 2, are also called discrete time Fourier transform pairs, right? So x of capital X of e power j omega is equal to sigma n is equal to minus infinity to infinity x of n e power minus j omega n, and this is 1 by 2 pi over integration over one period x of e power j omega into e power j omega n d omega. Now if you see comparison, so I'll go for CTFT and DTFT, discrete time Fourier transform, right? So if I want to find the Fourier transform, what we will get? X of j omega, which is minus infinity to infinity x of t power minus j omega t dt. In this case we will get the x of e power j omega, but summation will get, that is n is equal to minus infinity to infinity x of n e power minus j omega n. Now what happens to this x of t here, right? Discrete inverse Fourier transform 1 by 2 pi integration over one period, that is maybe 2 pi. So it is not over one period, sorry, it is minus infinity to infinity x of j omega into e power j omega t d omega. But in this case x of n is equal to 1 by 2 pi integration over one period x of e power j omega into e power j omega n d omega. Because this Fourier transform both are continuous in nature, so that's why we are getting the integration, right? So if it is discrete in nature, we should get the summation, but it is continuous in nature, so that's why we'll get both are this what you call integrations we are getting, because both are continuous in Fourier transform in the frequency domain, generally we say, right? So that is the somewhat differences between this continuous time Fourier transform, discrete time Fourier transform. So we can have a one word, that is, it is, what is this? This Fourier transform is continuous in nature, but aperiodic, right? Aperiodic. It's not a periodic, but this is, it is continuous. The Fourier transform is continuous and periodic also, and periodic. So this one is very important characteristics. So Fourier transform is, this is continuous time Fourier transform, and this is discrete time Fourier transform. So continuous time Fourier transform is continuous in nature but aperiodic, but a discrete time Fourier transform is continuous but and also it is periodic in nature. So that is somewhat differences, right? I hope you got some idea about this discrete time Fourier transform and what are the comparisons, etc. Now we'll start some basic signals, how to find the Fourier transform for the basic signals, right? That is what is the before we proceed there to find, we need to remember again. I will recall the formulas. When we do summations, we need three formulas. One is sigma n is equal to 0 to infinity, some a power n is there, so simply it is 1 minus a when a should be less than 1, right? Or we can say mod a also. 2 is n is equal to 0 to some constant n, and this is a power n only, so it will be 1 minus a power n plus 1 by 1 minus a. These formulas are from the mathematics subject only, right? So proof is there, so it's not required here. Again, the condition is a less than 1. The third one, suppose there are two limits minus n to n, or a 0 to n also no problem, and there is a 1, or we can say a. So a will be better, so it will be a into upper limit minus lower limit plus 1. So what is the upper limit n minus lower limit, that is minus n plus 1. So this will become a 2n plus 1. So these three are the important formulas when we solve any discrete time analysis, right? When we do any discrete time analysis, it may be convolution, it may be discrete time Fourier series, it may be discrete time Fourier transform, it may be jet transform also. So these three formulas are very important. Next we'll proceed to find the x of e power j omega or discrete time Fourier transform. So x of n is given, a of n, u of n. So we'll get what is the summation. So I'll write first formula, that is x of e power j omega, which is equal to sigma n is equal to minus infinity to infinity x of n e power minus j omega n. But if you see the limits, so u of n means it should be 0 to infinity. So the limits will change, which is n is equal to 0 to infinity. What is x of n? A power n into e power minus j omega n. Now if you see, this is power n and this is power n, so we need to take this n common, then it will become sigma n is equal to 0 to infinity a into e power minus j omega power n. So remember, whenever there is an exponential or the powers, so we can easily take common this power, any power we can take common, right? So because here n is common, then I am taking the common at the power is common, that is n, I am taking the out. So if I make this n is inside, so again it will become a power n into e power minus j omega into n, right? Now it's looking like the first formula, that is a power n is equal to 0 to infinity. So what is the value? Will get 1 by 1 minus a. What is a into e power minus j omega, right? So this is the discrete time Fourier transform of this a power n u of n. So if I take one more page, x of e power j omega is equal to 1 by 1 minus a into e power minus j omega. So we need to remember this basic signal transform always, as we remembered e power minus at into u of t in continuous time Fourier transform. And a here is less than 1. He said mod a less than 1, right? So a can be less than 1, a can be less than 0, or it may be positive, it may be negative also. Now the waveform of this discrete time Fourier transform. So we need to find, see, it is in complex in nature, right? So a into e power minus j omega, it is complex. So that means it will have magnitude as well as phase. To find the magnitude and phase, so what I will do is 1 minus a. So e power minus j theta means cos theta, that is cos omega minus j sin omega. So what it will be? So 1 by 1 minus a cos omega plus j a sin omega. So this is x of e power j omega. Now what is the magnitude I find? So the numerator only one term, so root of 1 square means 1 only, by square root of 1 minus a cos omega whole square plus a square sin square omega. So this is the magnitude we will get. So if I expand this one, what we'll get? 1 a minus b whole square, a square plus b square, a square cos square omega minus 2ab, so 2a cos omega plus a square sin square omega. So what is this one? Root of 1 plus a square. See, a square, if I take common in these two, a square, it will be cos square theta plus sin square theta, it will be 1. So minus 2a cos omega. So this is the magnitude. Similarly, if I find the angle from this equation, angle of x of e power j omega, the numerator will get 0 angle, but the denominator will get the tan inverse of imaginary part by real part. So what I will do, I'll take to the numerator, so 0 minus tan inverse of, whenever angle is coming to the numerator, so it will become just a minus, right? So angle can be shifted to either numerator or the denominator, etc. So only plus and minus will change. Tan inverse of the imaginary part is a sin omega by the real part is 1 minus a cos omega, right? Now this is the phase and this one is the magnitude. So to draw the waveforms, right, so the moment you see cos term and any sine term, that means these two are periodic in nature, right? So what is that period? Simply omega equal to 2 pi, right? If omega equal to 0, cos 0 is 1. If omega equal to 2 pi, it will become 0, right? So how to draw the waveform? Depending on the a, so we have to draw the two waveforms. So I'll draw for one. If a is greater than 0, the positive value of a, so what is the magnitude of x of e power j omega is equal to 1 by square root of 1 plus a square minus 2a cos omega. So if I take like this, this is omega. If I substitute omega equal to 0, cos 0 is 1, so 1 plus a whole square minus and 1 plus a square minus 2a. So at omega equal to 0, I'm substituting at omega equal to 0, so this will become, the magnitude will become square root of 1 plus a square minus 2a, because cos 0 is 1. So what is this value? A square plus b square minus 2ab. So square root of 1 minus a whole square, and this is 1 minus a, right? So when a is greater than 0, so we'll get 1 minus a at 0. So here the value is 1 by 1 minus a, right? Now if I substitute omega equal to pi, so what is the value we'll get? So 0, if I substitute pi, then 2 pi, etc. What is the values we'll see? If I substitute pi, cos pi is equal to minus 1, right? So whenever cos pi is minus 1, so it will become 1 plus a square plus 2a, minus minus 2 plus 2a. So it will become at omega equal to pi, so this will become 1 by square root of 1 plus a square plus 2a, because cos pi is minus 1. So this will become 1 by 1 plus a, directly written square root of 1 plus a square, so 1 plus a. So at omega equal to pi, because a is greater than 1 by more value, it will be less than this one. So here at omega equal to pi, we'll get, take one more thing, so we'll get 1 by 1 plus a here, right? Square will be cancelled. Similarly, if I find 2 pi, what is the value we'll get? So cos 2 pi again 1, so again we'll get 1 by 1 minus a. So again we'll get 1 minus a. So for 3 pi, we'll get again this value. Similarly, for negative values also, minus pi will get 1 by 1 plus a, and minus 2 pi will get same as 1 by 1 minus a. So the waveform will be looking like this, something like this. We need to go, right? So we can add like this. So it is a, what is this waveform? It's a periodic in nature. It's a periodic signal. Yes or no? And the limits are, maximum and minimum is 1 by 1 minus a and 1 by 1 plus a. Similarly, if I draw the angle x of e power j omega, right? So take one more sketch. This is omega. So what is the angle? So we got minus tan inverse of A sine omega by 1 plus 1 plus or 1 minus. 1 second. So it is 1 minus A cos omega. Now at omega equal to 0, so sine 0 is 0, cos 0 is 1. So 0 by anything 0, so we'll get angle is 0. When sine omega equal to pi, so sine pi means 0 again. So at pi will get again 0. Similarly at 2 pi I will get again 0. Similarly minus pi, minus 2 pi, etc. What happens when I substitute pi by 2, 3 pi by 2, minus pi by 2, minus 3 pi by 2, right? So what are the values we'll see. So anyway, we got 0 here, 0 here. What happens when I substitute pi by 2? Now a into sine pi by 2, so pi by 2 sine pi by 2 is 1, so you will get a here, and cos pi by 2 is 0, so we'll got the minus tan inverse of a. If a is greater than 1, so we'll get greater than 0 means we'll get some positive value, right? I mean, so this is tan inverse positive, so we'll get minus, so some value around minus, so it will be something like this, right? So again it goes to 0, again it will be minus, right? Next, if I substitute minus pi by 2 here, minus of minus sine pi minus pi by 2, so it will become minus a, so minus minus it will be positive, right? Something like this, right? So this is the phase of the Fourier transform, right? This is the magnitude, this is the phase. So for a less than 0, we may get opposite. So this will be down, this will be up. Here also, here this will be down, this will be up, etc. So you try to solve that one, right? Just we need to substitute omega values, pi, 2 pi, etc. Right? Again 2 pi will get 0. So this is the waveforms of this discrete-time Fourier transform, right? Next we will take one more signal, that is which is a two-sided signals, a power mod n when where mod a less than 1. Now to solve this, we need to see what is this, how to represent this a power mod n. So if I take the continuous time, that is e power minus a mod t, I represent it like this: e power minus a t when t greater than 0, that is u of t. When t less than 0, it will become e power a t but u of minus t. But in this case, somewhat different. For n less than 0, the signal will be stopped at that x of n can be written as a power minus n, right? So n is less than 0 means you get minus, but here u of minus n minus 1, because less than 0, after less than 0, the next integer is minus 1. So that's why it will be a power minus n u of minus n minus 1 plus when n is greater than 0, it is a power n simply u of n only. So this is the two-side sequence. How to draw this waveform? This is n, this is some x of n. So when n is equal greater than 0, right? So n equal to 0 means a power 0 1. I will get 1 here. Similarly, if I see here mod a less than 1, right? That means it may be 1 by 2, etc. So 1 by 2 power 0 is 1 only. If n is equal to 1, a power 1, so it will be reduced in amplitude because a less than 1. This is 1. Similarly 2, again it will be reduced, again it will be reduced, and so on. Similarly, if you see this one, a power minus n, when n is equal to minus 1, so what you will get? So this is anyway 1, a power minus of minus 1, again a, so we'll get same as this, again same as this, again same as this, and so on. Now it is a decreasing function. So as we see in continuous time, so it is a decreasing exponential when we talk about the continuous. So it is decreasing sequence generally, right? Or we can say exponential sequence also. So this is two-sided sequence. So how to find the discrete time Fourier transform? So this x of e power j omega will become So two-sided sequence, no? The summation will be splitted like this. Sigma n is equal to minus infinity to minus 1. Up to here only we need to a power minus n, and here e power minus j omega n, plus sigma n is equal to 0 to infinity. This is a power n, n is u of n is 1 only, into e power minus j omega n. So to solve this summation is very easy, but how to solve this summation? It should be, first we need to represent, this should be 1 to infinity actually. So minus infinity to minus 1, so it should be 1 to infinity. To make like that, what we do is substitute n is equal to minus 1. Let n is equal to minus 1. So this will become n is equal to infinity to 1. So but we have to write lower to higher. So the n is equal to 1 to infinity. So remember, I am substituting n is equal to minus n. Then it will become minus infinity to minus, minus of minus infinity to minus of minus 1. So that means infinity to 1. Infinity to 1 is not possible, because higher to, lower is not possible, lower to higher. So that's why I am writing the summation as 1 to infinity. Then a power, in place of minus n, substitute n. Again in place of minus 1, substitute n, plus sigma n equal to 0 to infinity a into e power j omega. I have taken common, so it is minus over n. Similarly, I can take a into e power j omega common, but n is equal to 1 to infinity, there is no formula. So to make that like that, so what we need to assume is, let n minus 1 is equal to k. Some different variable I am assuming. Now, when n is equal to 1, when n is equal to 1, k will become 0. Next, when n is equal to infinity, k equal to infinity, because infinity minus 1, infinity only. So the overall term will become like this. X of e power j omega is equal to sigma. Now it will become k equal to 0 to infinity a into e power j omega power n. See here, a into e power j omega whole power n. But what is n here? So n is equal to k plus 1. Right? This minus 1 is going that side. So in place of n, we need to substitute k plus 1 plus sigma n equal to 0 to infinity a into e power minus j omega power n. Now power k is okay, because k equal to 0 to infinity. A into e power j omega into power 1. So I can take common. So it will become a into e power j omega. And the summation will become a is equal to 0 to infinity a into e power j omega power k, plus sigma n is equal to 0 to infinity a into e power minus j omega power n. Now how to proceed? Now see, now the formulas are, as we have seen the formula, that is a power n or a power k, a power n. So a into e power j omega into 1 by 1 minus a. In place of a, we will get 1 minus a power e power j omega. Similarly here, 1 by 1 minus a into e power minus j omega. So this is the Fourier transform, discrete. But we need to simplify this one. So what we'll take is the LCM we will take. So this is anyway a into e power j omega, right? Now to solve this one, so first take a, this is e power j omega. So what we'll do, 1 minus a into e power j omega into 1 minus a into e power minus j omega. So a into e power j omega, this will be multiplied here, 1 minus a plus this one, 1 minus a into e power j omega. Now to solve this one, so in the numerator, a into e power j omega minus a into a square, e power j omega minus e power j omega, it will become 1, plus 1 minus a into e power j omega. These two will be cancelled, simple. And here we'll multiply 1 into 1 1 into a into e power minus j omega minus a into e power j omega minus minus plus a square e power minus j omega into e power j omega, it will become 1. So the numerator is 1 minus a square by here, so 1 minus 1 plus a square. So if I take minus a common, this will become e power j omega minus e power minus j omega. So not plus, say e power j omega plus e power minus j omega. I have taken minus out. So what is this actually? If I multiply with 2 and divide with 2, we'll get e power j theta plus e power minus j theta by 2. So this will become 1 minus a square by 1 minus, so this will become 2 cos omega into a, 2 cos omega into a plus a square, and here mod a less than 1. So this is the Fourier transform of x of n, right? So we need to remember this expression, that is a power mod n. So what is the discrete time Fourier transform? 1 minus a square by 1 minus 2a cos omega plus a square. Because this is a basic signal which is a two-sided sequence, so we need to remember 1 minus a square by 1 minus 2a cos omega plus a square, and the mod a should be less than 1. Then only this is possible, right? Similarly, we can see this is purely real term, right? There is no imaginary, so we'll get only magnitude term which is periodic in nature, that you can easily solve, right? So draw the waveform of this x of e power j omega. Next we'll see one more basic signal, which is rectangular signal. Now what is the value of this one? If you find the n is equal to 0 minus n1 plus n1, we'll get some sequence something like this. So how many impulses, we don't know. So this is x of n. So to find the Fourier transform of this signal, so generally we should get the sinc function, but we'll see what is the value we'll get. So again, x of e power j omega, I will write directly limits minus n1 to n1, this is 1 into e power minus j omega n. Now this is a power n is there, but these are the constant. So what we need to assume is, so this is n is equal to minus n to n. So let n plus n1 is equal to again some k. When n is equal to minus 1 n1, k will become 0. When n is equal to n1, k will become 2 into n1. So this will limit leads to k is equal to 0 to 2 n1, and it will become e power minus j omega. In place of n, what will get? K minus n1, right? So k minus n1, so minus n1 is a constant, so e power minus j omega into minus n1, so e power j omega n1 will be outside, and this will be k is equal to 0 to 2 into n1 e power minus j omega power k. Now we know the formula of this one, 0 to some n and a power n, so we'll get 1 minus a power n plus 1 by 1 minus. So from this, the x of e power j omega is equal to e power j omega n1 into 1 minus a. A means e power minus j omega power n plus 1, but here 2n1 is a n1, so 2n1 plus 1 by 1 minus e power minus j omega, right? Now, so this is the Fourier transform, but we need to simplify this expression. So what we need to do, see here, if I take inside e power j omega n1, e power j omega n1 minus e power j omega n1 into, if I split this one, so it will become e power minus j omega 2n1 into e power minus j omega by 1 minus e power minus j omega. Now the numerator will become like this, e power j omega n1 minus j omega n1 minus j omega 2 n1. So it will become simply e power minus j omega n1 into e power minus j omega by 1 minus e power minus j omega. Now to simplify further, so what we need to do? See, if you see carefully in the denominator, there is e power minus j omega. Here also e power minus j omega. If I take in the denominator e power minus j omega by 2 common, so what we'll get? So right here in the denominator I'm taking e power minus j omega by 2 common. That means we should get e power j omega by 2 here, minus 1 omega by 2 is gone, so it will be e power minus j omega by 2. Now similarly in the numerator also, if I take e power minus j omega by 2 common, then we can cancel. E power minus j omega by 2 is common, so it will be e power j omega n1 into e power j omega by 2, because I have taken minus j omega by 2 common. So if I want to cancel out, I should multiply with this here. E power minus j omega by 2 is taken out, so we should multiply with the same but opposite sign to make cancel. Minus e power minus j omega n1 into 1 by 2 is gone, so minus j omega by 2. Now I can cancel this 2 out. Now the numerator will become like this: e power j omega is common and it will become n1 plus half. Similarly, if I take minus j omega common, so minus j omega n1 plus 1 by 2 by, here same will be there, e power j omega by 2 minus e power j omega by 2. So if you see, e power j theta minus e power minus j theta, similarly e power j theta minus e power minus j theta. Now if I divide with in both numerator and denominator by 2j, so anyway 2j will be cancelled, I will get sine. So what is the value? J theta, so sine omega into n1 plus half by sine omega by 2. So this is the x of e power j. Again we need to remember this expression for rectangular signal in discrete domain, because so generally we will get questions from these rectangular functions in either a continuous time or a discrete time, so in gate exam. So that's why how to remember this one is very simple. In time domain, that is here n minus n1 to n1, there is a 1. So in discrete or Fourier transform is simply sine omega into this n1 plus half by sine omega by 2, right? So compared to this time domain, so it is not a sinc function, but it is a sine by sine omega into n1 plus half by sine omega by 2, etc. Right? So these are the 3 basic signals we need to remember for discrete time. The remaining we'll see, I mean in the table form. Directly we can remember the table to represent the discrete time Fourier transform. But we need to see the convergence of this discrete time Fourier transform. If we compare with the continuous time Fourier transform, so this should also follow the same conditions. That is, this x of n should be absolutely summable. That is, minus infinity to infinity. If I take the summation of x of n, it should be finite value. And the energy also should be finite. That is, minus infinity to infinity mod of x of n whole square less than infinity. And it should also satisfy the Dirichlet conditions. Right? So what are those Dirichlet conditions? So the first one is anyway absolutely summable. The second and third is there should be finite number of maxima and minimas. So the second one is finite number of maxima and minima in a finite interval time. Similarly, there should be finite number of discontinuities in a finite interval, and this discontinuity should be finite. So each discontinuity should be finite. So they should, anyway, digital conditions everyone knows. So these conditions also must be satisfied. If it is unbounded signals, so we cannot find this discrete time Fourier transform, right? In the next lecture, we'll see what are the properties of discrete time Fourier transform and some different problems we'll see.